Hello guys, in this video I will talk about hypothetical-deductive method in philosophy of science. We often think of science as a collection of facts, right? It is a list of observations about how the world works, like this falls when I do this, that heats up when I do that, etc. But what makes science so powerful is not observation alone. The real power of science lies in its ability to unify things. How does science unify things? It connects many different phenomena by explaining them through a small set of underlying rules. It takes 1,000 different phenomena and show that they're all driven by a tiny number of fundamental rules. And this power of science needs an explanation. We need to explain how theories can do this. And this is where the hypothetical deductive method comes in handy. This method is fairly common in science textbooks as a description of a good scientific procedure. The basic steps are as follows. First, gather some observations. Secondly, formulate a hypothesis that would account for the observations. Third, deduce some new observational predictions from the hypothesis. And four, see if those predictions are true. If they are true, go back to step 3. If they are false, regard the hypothesis as falsified and go back to step 2. Now, this method is usually taught as there's observation first, then you formulate a hypothesis, then you conduct experiments, and then you draw a conclusion. As you can see, this method treats theory as a deductive system. We can explain empirical phenomena by relating them back to general principles, which is similar to Euclid. But I think it is important to note that this is different than Cartesian mechanics, where principles are self-evident. Cartesian mechanics says that general principles rely on rational intuition. You accept a principle because it feels logically perfect, obvious, and undeniable to human mind. You don't need to test it against the world first. The hypothetical deductive method rejects this idea. The validity of principles rely on empirical consequences. A principle can only be valid if the predictions derived from it actually match our observations. Now, Euclid's theory is an axiomatic system. That is, it consists of a small set of postulates or axioms. These are propositions not proved in the system, but assumed to be true within the system. And theorems are derived from the axioms by deduction in accordance with the rules of logic. Hypothetical deductive method has a similar approach to how theories are tested and structured. There are hypotheses in theory which function as axioms because these axioms often describe underlying mechanisms that we cannot see, such as electrons. They cannot be tested directly. If scientific theories are mostly about things we cannot observe, how are they ever tested? How can we confirm claims about unobservable entities using observable entities? If you're an empiricist, you want to build theories by generalizing from what you see, which is induction. But there's a problem. Entities like electrons cannot be seen directly. The answer of the hypothetical deductive method is that the testing is indirect. It says instead of starting with the data, you start with a hypothesis and then deduce what would happen in the real world if that hypothesis were true. In this sense, scientists do not test the axioms themselves. Instead, they deduce observable consequences from them. We can't observe the axioms directly, so hypothetical deductive method relies on logical deduction here. Scientists deduce testable consequences from the hypothesis, just like we deduce theorems from axioms. Perhaps the most famous theory in physics to be presented as an axiomatic system was Newton's mechanics. The theory originally consisted of three axioms. These axioms or laws work together to explain vast array of phenomena. Before Newton, people believed the heavens and the earth obeyed completely different rules. Newton showed that they're all consequences of the same laws. From Newton's laws or axioms, scientists deduced theorems that explained everything from the path of a cannonball to the movement of the tides and the orbits of the planets. And these laws did not just explain the data, they allowed for the deduction of other major scientific laws too. For example, from Newton's laws, you could derive Kepler's laws of planetary motion and Galileo's laws of free fall. So, what have I said so far? Fundamental axioms often describe things we cannot see, therefore, they cannot be tested by direct observation. The hypothetico-deductive method says that we trust them not because we see the mechanism directly, but because the consequences derived from them match our empirical data. We can use kinetic theory of gases as another example. This is Rosenberg's example. As the 19th century progressed, chemists and physicists came to realize that gases are composed of vast number of molecules. These molecules are unobservable, but they are assumed to have the same basic Newtonian properties as ordinary observable objects, such as mass and motion. So the new idea was that heating and cooling a gas can be understood as changes in these Newtonian properties of the molecules, especially their motion, as they collide with one another and with the walls of the container. Heat, for example, is the macroscopic reflection of molecular motion. The development of these ideas produced the kinetic theory of gases, and some of the hypotheses or axioms of this theory are gases are composed of vast number of molecules, which are perfectly elastic point masses. These molecules obey Newton's laws of motion. They exert no forces on each other except during collision. Now, there are other hypotheses like the one that says temperature of the gas is proportional to the mean kinetic energy of the molecules. The important thing here is that you cannot derive this from looking at a gas. You have to assume them as your starting point, and you have to deduce some consequences from them. Indeed, from these assumptions about unobservable particles, scientists mathematically derived the ideal gas law. And since the ideal gas law is confirmed by experiment, the unobservable hypothesis about molecular motion is accepted as the correct explanation. We cannot see the molecules or directly test the claim that they are perfectly elastic. However, because we can logically deduce testable laws from these hypotheses, we can consider the hypothesis confirmed. The core achievement of the theory is connecting these unobservable properties to the macroscopic things that we can measure, such as temperature, pressure, and volume. Because we can collect instrument readings for things like pressure, volume, and temperature. These are measurable things. We can use tools to get numbers for these three things. And any law that describes how they relate to each other is empirical and directly testable by experiment. For example, there's Boyle's law, which can be derived from the kinetic theory of gases. It simply says that if you squeeze a gas, its pressure goes up, and if you let it expand, its pressure goes down, as long as the temperature stays the same. So the kinetic theory basically explains what we see in our experiments. Think about when we're checking a tool to see how temperature or pressure changes. Those things We can actually, those are the things that we can actually measure. But theory explains those results by talking about things we cannot see. Essentially, it uses the unobservable world to explain the observable one. So you start with assumptions about molecules and their motions, and then from these you deduce observable consequences which are testable because they are about things like pressure, volume, and temperature. So confirmation then works by successful prediction. The hypothetical-deductive method can also be seen as an analysis of how theories are confirmed, because when the deduced consequences match our observations, the hypotheses are, are, are directly confirmed. If they fail, the theory is disconfirmed or revised. Hempel provided the key account of hypothetical deductive method using the historical case of Ignaz Semmelweis and childbed fever. The process goes like this. Um, in the 1840s, a woman in Semmelweis's hospital were dying of childbed fever at a terrifying rate, and he needed to find the cause. So Semmelweis proposed the hypothesis that the fever was caused by cadaverous matter, which is particles from dead bodies, being carried on the hands of medical students. And he reasoned, if my hypothesis is true, then if the students wash their hands in a strong cleaning solution before touching the patients, the rate of childbed fever must decrease. And he forced students to wash their hands and observe the results. And the outcome was that the death rate dropped dramatically. Hempel said that uh, this does not mean that the hypothesis is true or proven, it just means that it is supported or confirmed. The fact that the fever dropped confirmed the hypothesis, but it didn't verify it as 100% true. And now that we have mentioned confirmation, let's talk about the differences between Popper's falsification and hypothetical deductive method. The similarity with Popper is that both involve deducing observational consequences from a hypothesis. A falsification is also deductive. The main difference is that Popper rejected the confirmation aspect of hypothetical deductive method. For Popper, the importance of deduction was not to support a theory, but to provide a way to refute it. He argued that while you can never prove a theory to be true, yeah, you can prove it false. No matter how many white swans you see, you can never prove the rule all swans are white. Falsification, on the other hand, is certain. Finding just one black swan proves the rule is false. And this is a solid deductive inference. So, hypothetical deductive method says that science proceeds by the generation of hypotheses from which predictions are deduced that can be tested by experiment, but this idea can be cashed out in inductivist or falsificationist terms, depending on whether we accept confirmation or not. There are different formulations of hypothetical deductive method, but the version I'm talking about in this video is basically the same as Popperian views, but with a more positive and less skeptical view about confirmation. So in this hybrid version, the method agrees with Popper on how science works, but disagrees with him on what the results mean. So if the prediction succeeds, you get to say the theory is supported or confirmed, whereas Popper's view is that a theory cannot be confirmed. We can never have a positive reason to believe that it's true. Now let's look at some of the other criticisms of this method. When you give a method of science, you are sort of saying what science is and what science is not. Then you get people in alternative fields using these ideas to prove that they are scientific. They'll say, hey, we're using the hypothetical deductive method, so we are just as scientific as a physicist. It's a way to defend what they do. But aside from that, even among real scientists, this creates a bit of a hierarchy. Many argue that the hypothetical deductive method is superior because its conclusions follow necessarily from premises. So, if you have this as a standard, then fields that just observe and describe things like epidemiology often get treated like second class sciences compared to lab sciences because they seem to be relying on induction rather than rather than the deductive character of the hypothetical deductive method. Well, science varies so much that maybe any single definition of method is creating problems. If you look at the practice of the working scientists, a marine biologist and a theoretical physicist look like they are doing completely different jobs. When you ask a field biologist what they when you ask field biologists, for example, what they might consider their method to be, they will tell you things which include years and years of passive observation of animals. Then they reach a conclusion. But when you ask a theoretical physicist the same question, they might include mathematical derivation on a chalkboard without any observation yet. So, in the case of biology, the method may be more inductive and data driven than the math of physics. Another problem with physics is that in modern high level physics like string theory, scientists sometimes move away from hypothetical deductive method because they can't even test the predictions yet. Instead, they justify their theories based on mathematical beauty or simplicity, which is a huge departure from the classic hypothetical deductive rule of test it and see. Okay, now let's talk about the Raven problem. First, let's assume we have a hypothesis that says that all ravens are black, right? To confirm this, you would go out, look for ravens, see one that's black, and boom, evidence, right? Each black raven observed removes one possible way the hypothesis could be false. But the paradox is, imagine you're in a room with no ravens and you see a red bottle. Well, that's not a raven, and it's not a black raven, it's not black. Logically, that's still evidence for the same theory, which is weird. All ravens are black is logically equivalent to all non black things are not ravens. A red bottle is not black and not a raven. So it confirms the hypothesis that all non black things are not ravens. And by equivalence, it confirms all ravens are blacks. And this leads to the absurd result that you can confirm ravens by looking at bottles, right? So this is the ravens problem or the ravens paradox. When I first read this, I did not see any problem at all, actually. I was like, yeah, whatever, why not? It does confirm all ravens are black. It does not mean that we should go and look for non black things that are not ravens. It, it means that there is a little bit of confirmation coming from that red bottle, and that's all. And clearly, I was thinking like Hempel. He says, yes, a red bottle or a white shoe confirms that all ravens are black. It confirms that ravens are black, but it does so only by a tiny amount. So when you say all ravens are black, you say all Fs are G, right? Hempel pointed out that, logically speaking, the statement of all Fs are G is not a statement about F, but a statement about everything in the universe. In other words, it says that if something is an F, then it is G. Objects that are not F are not entirely irrelevant. They are part of what makes the statement true. There's another solution which is good solution. It suggests that an observation only counts as confirmation if it arises during a genuine test. A genuine test is the test where the theory could have been proved wrong. For example, imagine two scenarios. In scenario A, I say, I have a raven behind my back. If you look and it's white, the theory dies, right? If it's black, the theory is confirmed. In scenario B, I say I have a black object behind my back. If you look, it might be a raven or a shoe or anything else, but neither of them refutes the theory that all ravens are black. Therefore, this observation adds no value actually. So, why doesn't scenario B count? Because when someone says, I have a black object behind my back, want to see if it's a raven, you already know the object is black. And I don't have to think that all black things are ravens. The only thing that kills my theory is a white raven. And it's impossible for the object behind my back to be a white raven because we already know it's black. Since there isn't any chance that this specific observation could refute my theory, the test is not a genuine test in scenario B. But this test is not relevant to my investigation about black ravens, right? If he pulls out a raven, we have a black raven. This fits my theory. And if he pulls out a shoe, we have a black shoe. This also fits my theory. This is not a genuine test. So this solution says that perhaps there is only confirmation when the observations arise during a genuine test. Another problem with hypothetical-deductive method is underdetermination problem. Underdetermination says that there might be theories that are empirically equivalent but theoretically incompatible. So just because a theory makes a true prediction doesn't mean that it is the only theory that could have made that prediction. For example, you have theory A that makes some predictions. Then you have theory B, it makes the same predictions but suggests a completely different underlying mechanism. The problem is, if they make the same predictions, the evidence cannot tell you which one is the right theory, right? Now, underdetermination is mainly discussed in scientific realism debate, actually, but I think it is also relevant here because if different and incompatible theories can entail the same confirmed predictions, it means that the hypothetical deductive method cannot use empirical success to favor one theory over its rivals. Another problem is the Duhem-Quine problem. According to this problem, a hypothetical deductive method is not really saying much. Uh, the problem is that we know that a hypothesis never yields testable consequences on its own. You always need some auxiliary hypothesis or background assumptions. Hypotheses, Duhem claimed, are never tested in isolation. Any attempt to confront a hypothesis with empirical results takes for granted auxiliary hypotheses that may be revised if things go wrong. When a test fails, logic doesn't tell you what went wrong. To make a prediction, you need a theory plus a bunch of extra assumptions, like the assumption that my equipment is working right now. The problem is that if the prediction fails, you don't know if the theory is wrong or if one of those extra assumptions was wrong. You can always save a theory by blaming the equipment at your hand. Now let's talk about another problem. Hypothetical-deductive method gives us a direct path, right? You have a hypothesis, you deduce a prediction, and then you test it. Ian Hacking, in his book Representing and Intervening, says that maybe theoretical statements do not directly entail observable claims. You cannot deduce experiments straight from the core theoretical principles because the core propositions of physics are too abstract and don't actually link to anything you can see. So deducing an experiment from such a high-level theory may not be possible. In this case, when you have hypotheses which are purely theoretical statements, you also need a semantic bridge to connect theoretical terms to observational ones. And this is where models come into play. Model building lies between theory and phenomena. The process of model building is neither pure theory nor a direct description of the world. A model is something between theory and reality. It is an intermediary that connects theory and phenomena or the world. In science, we often have to create a simplified and idealized versions of the world, and and we call them models. Of course, the word model means different things in different fields of science. In biology, you can build concrete models out of wire and plastic, whereas in physics, they might still be conceptual, but still less abstract than the core hypotheses of the theory. But anyways, we are not deducing tests straight from theory. Theory can be too complex for us to do that, so we create tractable models as intermediaries. We can only deduce and test the consequences of the model. So it looks like scientific reasoning is more about building and simulating models than the simple recipe of the hypothetical-deductive method. But I think this doesn't show that the hypothetical-deductive model is wrong in any way. It only says that it is incomplete, maybe. All right, guys, that's it for this video. See you in the next one.